Let's have a look at that exercise 8. Okay, so it's we have Laplace equation, which is something like the heat equation, so Laplacian of u, happening inside of a square of size 1. Okay, so what does that mean? It means that our domain is actually a square. Inside of that, I've got that Laplacian of u is equal to 0. What does that mean? Laplacian of u, that's just d2u over dx2 plus d2u over dy squared. Okay, that's it's only in xy, so space variables, no time variable. Okay, so what we want is to get something like the steady state of this equation when we are given some specific boundary conditions. So what are these? So let's see them one at a time. First one, u of 0y is equal to 0. U of 0y means that side. Okay, so I've the usual x horizontal and y vertical. U of 0y is equal to 0, so that means u is equal to 0 constantly on that border. On this side, the other one, okay, u of 1y, all right, so that's exactly this one. Okay, when x is equal to 1 and y goes from 0 to 1, I keep my u value at 1. Okay, and I also have two more conditions, so that's maybe a bit unrealistic, but then it's really a pedagogical example so that you can understand what's happening here. U of x0, so anything happening on that bottom line is going to be equal to x, right? And on the top one, u of x1 is going to be equal to x2. Okay, so like you hit in two different ways the bottom and the top one. I'm talking about bottom and top at 12. It's just a plane, all right. So that lower part and that higher part in y, and in one sense it's just a linear hitting. So u of x0 is equal to x, and on the top one is just going to be a parabolic. All right, so that's the other one. So this is it. We're going to actually do that in two ways, right? Well, in two ways. No, we need to do it in two different parts, and then we are going to sum our solutions and to obtain the complete solution, right? So let's have a look at that first part. We want, so same equation, let us rewrite this equation. So d2 u over dx2 plus d2u over dy squared is equal to 0 with the boundary condition. So kept at 0 on the, so we've got this one, right? So we've got this one. U of 1 is equal to 1. We also have this one. And we have, and we're going to have 0 and 0 also for those ones. Okay, so these 0 and 0 also on the top. Okay, so actually it's something like it's insulated on three sides and it's kept at 0 here, here, and here. And here I've got some constant value equal to 1. So we've got something like heating, constant heating on that side. Okay, so the idea is to use separation of variables. So let's just write what we have. Okay, so separation of variables, it just means that we're going to assume that u of xy is going to be a function of x and a function of y. Okay, so as usual, we're going to write this. So that gives us second derivative in x is just x second times y. Second derivative of y is just x times y second is equal to 0. So we are going to really have something like x second over x is equal to minus y second over y is equal to, well, this is always the question. What should we use? Should we use a lambda? Should we use a minus lambda? That's a very interesting question to ask. Okay, so and you will see what's happening. Okay, so first choice, we'll proceed to them both. Minus lambda with lambda positive. Okay, so let's write what we get if we do this choice. So what's happening then? I get that x second over x is equal to minus lambda, y second over y is equal to lambda with lambda positive. That means my x second over x is just going to be gives me, characteristic equation. Rho square is equal to minus lambda, so that means that I have, maybe I could write it, rho square is equal to negative lambda, so negative sign, so I've got my roots are plus or minus I square root of lambda, so that my x is going to be written as a composition of cosines and sines. Okay, so a cos square root of lambda x plus b sine square root of lambda y. Okay, on the other hand, with the same choice, I'm going to have characteristic equation for y, rho square is equal to lambda being positive, so that has some positive roots, real roots, sorry. So r is equal to plus or minus square root of lambda, which happens. And then I can write that my y is it's going to be a composition of exponential raised square root of lambda times y and exponential minus square root of lambda times y. The habit in that kind of problems is to write these using the cos h and sin h, because the cos h, you would have something like c plus d, this thing, and we're just going to write this as c prime exponent cosine h square root of lambda y plus d prime sine h square root of lambda y. But this is really just a writing, okay? I can recombine my exponentials in order to create cos h and sine h's, all right? So let's say that then my y is going to be written as c cos h of square root of lambda y plus d sine h of square root of lambda times y. Okay, what's happening then when I'm trying to plug in the initial conditions? Right, yeah, well, the boundary conditions. So my boundary conditions are going to be, so remember, maybe we can start with the first one, u of 0y, so the left side of my vessel is kept at 0, u of 0, y is equal to 0. What does that mean? It means that x of 0, y of y is equal to 0 for any values of y. So x of 0 being a times y of y is equal to 0 for all y. That means a is equal to 0. Okay. Then what do I get? U of x0. Well, I can actually take them in any order that I would like. Okay, let's take the 0 ones that are going to be more nicer. Okay, so I've already gotten rid of the a. Right. Next, I'm going to apply u of x0 is equal to 0. So u of x0, so that means for y is equal to 0, I've got this kept at 0. Okay, so u of x0 is equal to 0. That means that x of x times y of 0 is equal to 0. Okay, so what do I get? I get in particular that I need my, this is actually the sine h of 0 is equal to 0, so I'm only getting the c, which, well, the y of 0 is just c, so I get that c x of x is equal to 0 for all x. That implies that c is equal to 0. Okay, up to now, that's just what we would expect. Okay, so I'm left with just a b square root of lambda y and d sine h square root of lambda y. Okay, sorry, that was an x here. Square root of lambda times x and the d sine h square root of lambda times y. Okay, so let's write it. U of x y, so it still depends on lambda and my constants. It's just going to be b times d, so that's just making a big constant, so let's call that b prime, sinus of square root of lambda times x times sine h square root of lambda times y. What else do I have? I have that u of x1, meaning the top part of the vessel, this one, u of x1, is also kept at 0. So what does it mean? It means that for y is equal to 0, I get that, so for y is equal to 1, I get that sinus of square root of lambda x for any x times the sinus of square root sine h of square root of lambda b times d, so well, I said I would call that b prime, is equal to 0 for every x. Okay, so what would be the only possibility? Well, I've got two possibilities. As it must work for all values of x, it must be either square root of lambda is equal to 0, or that means lambda is equal to 0, or d prime is equal to 0. Okay? In any cases, what does it imply? It implies, in any of those cases, it implies that u of xy is now equal to 0 for all x and all y. Okay, and why is that a problem? That's a problem because I've got the last boundary condition, this one, okay, the one that it says it's kept at 1 on the right side, so u of 1 y is equal to 1. I will never be able to fit that one if my solution is always constantly equal to 0. Okay, so if you make the wrong choice, it's going to appear at some time that it's not working. Okay, so my choice, let's keep minus lambda with lambda strictly greater than 0, does not work here. All right, and you realize it's not working because you get a constantly equal to 0 solution and no way to adjust then your boundary condition. Okay, so let's now make the right choice, meaning so that's wrong choice. We should choose lambda plus lambda with lambda positive. Okay, so that makes my equation x second over x is equal to lambda, and minus y second, minus y second over y is equal to lambda. Okay, so next video, maybe you can try it by yourself, and next video to make that.